All right, so we know how to calculate fluxes. Let's go back to why we even invented this concept. We invented flux, or we've come up with this definition, so that we can figure out a way to relate this quantity, relate this flux, which has to do with the electric field, the direction of the electric field, and the area, to the charge inside. And so that leads to a physical principle that's called Gauss's law. Gauss's law says that the sum of the electric flux, the sum of E dot n hat delta A over a closed surface, like a box that we've just been showing, is equal to the charge inside divided by a constant. And that constant turns out to be epsilon 0. And remember, epsilon 0 is 8.85 times 10 to the minus 12 coulombs squared per Newton meters squared. Okay? So this is exactly what we were gearing up for. We have a quantity now which tells us that some relationship between the electric field, the area, and the direction, when you add it all up over the closed surface, tells you about the charge inside the closed surface. Okay? So when we had the case of the positive charge inside, that first example we looked at, let's do this. So here was our box again. And we had electric field that was pointing toward the outside of the box. Okay, so something like that. What I have to do is add up the electric flux over the entire surface, and that will tell me something about the charge inside. Well, I have to know the direction of n hat, and on the top surface n hat is that way, on the side n hat is that way, on the bottom n hat is down, on this side n hat is that way because it's perpendicular to the surface and pointing towards the outside, right? And on the front n hat is pointing which way? Towards us, right? Towards you guys. So let's look at this. If we look at the flux on this surface, is it going to be positive or negative? It's positive, right? Because the electric field has a component in the direction of n hat. The flux on the top is going to be what sign? Positive. Flux on this side is going to be what sign? Flux everywhere is going to be, for this example, what sign? Positive. So that's telling us that there is what sign of charge inside? Positive charge, right? Opposite case, when we had the negative charge inside, the electric field was pointing towards the interior. That would have given us a negative flux because E and n hat would be in mostly the opposite direction. And then when we had the case of the capacitor, you had electric field on one side pointing in this direction. So the flux on this right side was what sign? Positive. The flux on the left side was what sign? It was negative, right? Because the electric field was pointing in, n hat was pointing out. So that was in the opposite direction. What was the flux on the top? Flux on the top was 0 because what was the angle between the electric field and n hat on the top? It would be cosine 90. Cosine 90, right, which gives you 0. Okay? So we see how this works. And this summation of all these fluxes over the surface is going to give us some idea of what charge is inside. Let's see if we can try a quick example. Okay, so here's kind of an arbitrary example, but let's say we have over the right side of this box an electric field pointing to the right, magnitude 1,000 volts per meter. Top, bottom, front, and back, let's assume the electric field is the same over those surfaces of 800 volts per meter, again pointing to the right. And on the left side, the electric field is 400 volts per meter, again pointing to the right. Here's the dimensions of the box. It's 3 centimeters high, 2 centimeters deep, 8 centimeters long. See if you can calculate the net electric flux over the entire surface. So we have essentially 6 surfaces to think about, right? Front, back, top, bottom, left, and right. You want to find the flux on each surface, add them all up to get the total. All right. So we didn't have a chance to calculate it, but let's just go through it. Let's just go through it real quick. What's the flux going to be on the top? 0. On the bottom, front, on the front surface, the flux is going to be 0 again, and on the back, still 0, right? Because everywhere on those surfaces, the electric field is parallel to the surface, but perpendicular to the local unit normal vector, okay? So they're all going to give you a flux of 0 because we have a 90-degree angle between those vectors. On the right side, we're going to get a positive or negative flux. Positive flux, let's just see if we can find it real quick. We would have the electric field magnitude times n hat magnitude times the cosine of 0, right? Times 0.02 times 0.03. So what was it, 1,000? So we get 1,000 volts per meter times 0.02 times 0.03 is what? 6? Is that 6? 0.6, thank you. 0.6 volts times meters. What about on this side? What do you get? What's the sign? It's negative 0.24, right? You get negative 0.24. That's coming from, what was the sign of what was the magnitude? 400 volts per meter. So you can do it in magnitudes. 400 volts per meter times the cosine of 180, which is negative 1, times 0.02 times 0.03 gives you negative 0.24. Negative 0.24. And so when you add those up, you get 0.36, right? Answer number 2, okay? So next time we found the flux, we could then use this to calculate the charge. We'll do an example of that next time.